In this video, we will discuss the role of symmetries of a Hamiltonian in generating different conservation laws. Particularly, we will look at the translational symmetry and the rotational symmetry and the conservation laws that exist because of these two symmetries. So let's begin with the translational symmetry. So assume that we have two particles, let's say particle of mass m1 and m2, and we're interested in studying their dynamics. We can see right away that if we translate both particles by some, let's say, constant vector A, and take these particles here, m1, m2, we see that the physical situation does not change at all. And this type of symmetry is also reflected by this Hamiltonian, and this gives rise to the conservation of linear momentum. Let's see how. The Hamiltonian of these two particles can be written in a couple of ways, but if we write it in terms of a coordinate system in which we have one relative position vector r, which is the position of this mass with respect to this, and the position of the center of mass of these two particles, then we can write the Hamiltonian as like this, where this is the total mass m1 plus m2 of the system, and this is the total momentum of the two particles, whereas this is the relative momentum, the total momentum in relative coordinates, and this is the reduced mass, and this is the potential between the two particles. So, translating these two particles by a constant vector A can be represented by a translation operator, let's say T of A, when it acts on any composite state, let's say R1, R2, it takes the position of both particles and translates it by a constant vector A. Note that both R1 and R2 are translated. It's not just if we translate only one and not the other, then of course the problem is changed because the relative distance between the particle is changed. So the translation symmetry is preserved only if we translate all the particles by the same distance along the same direction. That is, we translate it by a constant vector A. So this translation operator can translate a position state of two particles like this. So let's see under this translation what happens to this Hamiltonian. To do this, let me go through all of these terms one by one. So this term P square, so let's begin with the classical counterpart. It is the total momentum, P square. So this is nothing but P1 square plus, sorry, not P1 square, P1 plus P2 whole square, because we find the total momentum first and then there is a square. And these momentums are M1 R1 dot M2 R2 dot whole square. Now, what happens to this momentum under translation? So, in the translated frame, both R1 and R2 has to be translated by a vector A. So let me just write this translated total momentum. This would be M1 R1 plus A1 dot plus M2 R2 A2 whole dot and then square. Now you see this derivative will have to be taken of both of these factors individually, and since this is a constant factor, their derivative will be 0, and we will be left with m1 r1 dot plus m2 r2 dot whole square, which is nothing but this p square. So it means this, and since this mass is independent of the coordinate, so this term, when it translates under this translation operator, remains the same. Let's come to this relative momentum term. So this momentum p square is the momentum of both particles, but the momentum of first particle would be 0 in this frame because its sound position vector with respect to itself is 0. So m1 0 plus m2, the momentum of this particle is r2 minus r1 whole square. So this is 0, so we are left with m2 square r2 dot minus r1 dot square. So let's see how it translates under the translation operator. So the translated relative momentum is m2 square. We have to translate r2, so r2 becomes r2 plus a minus r1 is r1 plus a whole square. So again these derivatives are 0, so we are left with m2 square r2 minus r1, which is the same as the original p. So both of these terms, when they are translated by a constant distance a, they remain the same. Let's now see this potential. The potential between two particles, if both particles are charged, is r2 minus r1 mod square, no mod square, and 1 over 4 pi epsilon naught q1 q2. Now this r2 changes to r2 plus a, r1 changes to r1 plus a, and there's a minus sign here, so this is r1 minus a. Now these a's are cancelled, and we have the same potential as before. So let's say this was the potential, so this is the translated potential, and the translated one is again the same as the original potential. Okay, so actually it's only function of the magnitude. So we see that the Hamiltonian remains the same independent of this translation. So it means that Hamiltonian and the translation operator, they commute with each other, and since this translation operator is generated by the total momentum of the system, total linear momentum of the system, it means that Hamiltonian and the total momentum operator, they commute. So we have this important result, that Hamiltonian and the total linear momentum operator, they commute with each other. Now we can use this knowledge to find the time rate of change of the expectation value of total momentum and see if it changes with time or not. For that, recall that if we have any operator, for any operator A, the expectation value of the time rate of change of the expectation value of A is the time rate of change of expectation value of this operator is given by this expression, which we can show from the Schrodinger equation that this relation is true. So let's use this to find the time rate of change of the total linear momentum of two particles with this Hamiltonian. So with this Hamiltonian, we know that our two particle Hamiltonian commute with the linear momentum, and linear momentum is independent of time, and this is zero as well, just as we saw earlier. So this means that expectation value of the total linear momentum does not change with time. Sorry, not zero but constant. And this is what is the statement of the conservation law of linear momentum in quantum mechanics. So what we concluded that for any Hamiltonian which commutes with the total momentum operator, that system has a constant value of the expectation of the linear momentum for that system. So you see that this statement is slightly different than the classical statement. In the classical physics, what we say that the total linear momentum of the system is constant. But here it's not the total momentum that we are saying is constant, but the expectation value of the total momentum which is constant. Okay. So now we see that the translation operator commutes with Hamiltonian, so the momentum operator commutes with Hamiltonian, so the expectation value of linear momentum is constant. Let's now see another very important translation symmetry of the Hamiltonian, which is the rotational symmetry, a rotational invariance of the Hamiltonian. As we see that our Hamiltonian only depends on the lengths of different vectors, and let me just write it again here. So our Hamiltonian has total momentum, has relative momentum, has potential, which is function of the length only. So if there are these two particles, M1, M2, this is the relative position vector, and this is the position vector of the center of mass. So let's see if this Hamiltonian commutes with some rotational operator or not. For that, let's choose the z-axis as the axis of rotation, and then we can generalize to any axis later on. So rotation about z-axis. So suppose we have a rotational operator which rotates by a small angle d phi around z-axis. Let me write this with the k vector here. So this is the rotation vector, and we will see that it has a generator, which is the orbital angular momentum. And what we are going to see is if this rotation operator commutes with this Hamiltonian, it would mean that the Hamiltonian commutes with the generator of this rotation, which is the orbital angular momentum. Then it would mean that the angular momentum is orbital angular momentum is conserved, because if Hamiltonian and that orbital angular momentum operator commutes, then using a similar equation like this, we can show that the orbital angular momentum is also conserved. So while discussing rotations, in addition to selecting an axis of rotation, we also have to select the origin of the rotation. So for these rotations, let's assume that we are rotating around the center of mass, so that we are not worried about the net rotation of the particles, but by keeping the center of mass fixed, the rotation of the particles around this center of mass point, which essentially means only rotating this relative position vector r and keeping this vector the same. To understand the rotational symmetry, let's consider this coordinate system. Let's suppose we have x, y, and z, and there is this position vector r with coordinates x, y, and z, such that this is angle theta, and if we project this vector in the xy plane, the angle made by this projection vector with the x-axis is the angle phi. So it means, and this length is r, that x can be written as r. So this is r vector. If you project it here, this would become r sine theta. So this is r sine theta, and if you project this r sine theta onto x-axis, we get r sine theta cosine phi. Similarly, if we project this r sine theta onto y-axis, we get r sine theta sine phi, and z component is simply the projection of this vector onto the z-axis, which is r cos theta. So we have this vector r, whose position, whose coordinates x, y, z are defined by here. So when we apply the rotation vector r to this, suppose that this is and we are rotating around the z-axis. So this is the vector r, and we are rotating it around z-axis like this. And if we apply a small rotation around z-axis, so this vector goes from here to here. This angle with the z-axis, of course, remains the same, because if this is z-axis, we are rotating this vector around it, so the angle between the vector and z-axis remains the same, even though unfortunately I cannot show on this 2D board. But the vector of the projection in this xy plane will have a different angle, and suppose now this projection is rotated by this angle d phi, and because of this, the projection on x-axis change, the projections on y-axis change, but the component of the rotated vector along z-axis remains the same. So let's work out what are the components of this vector after rotation. Now, before rotation the angle was phi, and after rotation the angle is phi plus d phi. So x component becomes r, x is equal to r sine theta, because theta is same, cos phi plus d phi. Let's open this up using cos alpha plus cos beta formula. So this becomes cos phi cos d phi minus sine phi sine d phi. Since d phi is small, we can take this to be roughly 1. This becomes r sine theta cos phi, and this becomes minus r sine theta sine phi, and let's approximate this sine d phi with just d phi because d phi is small. This becomes, this r sine theta cos phi is nothing but x, older x. So let me call this x prime. So this is x, and this r sine theta sine phi is older y, minus y d phi. So after rotation, the coordinate becomes x minus y d phi. Let's see what does y become. So y becomes y prime r sine theta sine phi plus d phi r sine theta sine phi cos d phi plus sine d phi cos phi r sine theta sine phi. This cos d phi is roughly 1 when d phi is small, so this becomes r sine theta sine, so this sine d phi can be approximated just as d phi. This is cos phi. So r sine theta r sine phi is the older y, and this r sine theta cos phi is older x, so this becomes this. So y prime is this. Z prime remains z because theta doesn't change. So after rotation, z prime and z are the same. Therefore, we have new coordinates of our vectors after rotation by an angle d phi. So let me write it using bracket notations. So if I apply this rotation operator around z axis by an angle d phi on a state xyz, what we get is this, that x goes to x minus y d phi, y goes to y plus x d phi, and z remains the same. And if we look at this, this is nothing but translation of x by this amount, translation of y by this amount, and z as it is. So it means I can equivalently write it using translation operator. Along x-axis we have minus y d phi. Translation along y-axis is by the amount of x d phi, j unit vector, and x, y, and z. So it means I can write this rotation operator in terms of the two translation operators. Now I can use their generator form. So in terms of linear momentum, this small translation can be written as being generated by 1 minus iota over h cut p x y d phi, and this can be written as 1 plus iota by h cut p y x d phi x, y, and z. And if I multiply them and neglect this d phi square term, we will get 1. This into this is minus iota by h cut. D phi is common, so I get px y, and here pyx. So I get minus sign from here. I took minus common. Pyx xy z. If I define another operator, let's call it Lz, such that Lz is minus pxy plus p so it's better if you put consistently the operator notations here. Okay, so this is pxy plus pyx. So if I define a new operator Lz as this, then I can write my rotation operator d phi k as 1 plus iota by h cut Lz d phi x y z, where now this Lz operator is the generator of rotation by amount d phi, and this operator Lz is called the component of orbital momentum, the z component of the orbital angular momentum operator. Similarly, if we had started with, let's say, rotation around x-axis, we would have to define, we could have found another operator which was the rotation around x-axis, that would have been the component of x component of angular momentum and so on. Since there are three orthogonal directions possible in 3D space, we have three component of the orbital angular momentum operator L, and this is just the z component of the operator. So now we have this new operator Lz, which generates the rotation around z-axis by an amount d phi, if we define it like this. Let's now see if this operator commutes with our Hamiltonian or not, because if it commutes, then we can develop the law of conservation of angular momentum. To do that, but before I do, let me just take a quick digression here. So we know that linear momentum in classical mechanics is p, and orbital momentum in classical mechanics can be defined as r cross p. Which means that if we want to, we can use postulates of quantum mechanics, where we know that we can translate the observable from classical mechanics to operators in quantum mechanics. So we can define the orbital angular operator L directly from this equation, where this is the position vector, this is the linear momentum vector, and if we convert them into operator, we can get the orbital angular momentum. And if you do expand it like this, the z component of this vector is indeed this vector written over here. So we can find the orbital angular operator by from the classical mechanics by converting the observables into operators. Okay, so let's now see if this rotation operator and subsequently the angular momentum or orbital angular momentum operator commutes with the Hamiltonian of two-particle system. Okay, so let's now develop the commutator of our Hamiltonian and the orbital angular momentum component along the axis. So this is our goal that we want to find. Okay, and just to recall, the Hamiltonian is total momentum square plus relative momentum, reduced mass, and the potential. Now we can see right away that this Lz and this commute. The reason is that we define the rotations with respect to the relative position vector r by keeping the center of mass fixed. So this commutator is 0 just to begin with. And we are only left with finding the commutator of Lz with p square and with the potential. To find the commutator of LZ with P squared, we need to evaluate this thing, which is Px squared, Py squared, Pz squared, and to evaluate, which can be written as Lz Px squared plus Lz Py squared plus Lz Pz squared, and so on. So this is what we need to find, and to find them we first need Lz Py, Lz and so on. So to do that, let's begin with this thing. So this is the first commutator that we are going to find. So Lz is minus y px plus x py px, and just remember this ypx can be interchanged and xpy can be interchanged because x and py commute, y and px commute. So I can write this as minus y px plus x py px, and this would be 0 because px commutes both with y and it commutes with itself, so this is 0. I'm only left with this, and this I can expand x py px plus x px x and py. So this py goes here and this x comes here, and this is 0 because we already know py px commute, so this is 0, and this is iota h cut, so this becomes iota h cut py. So Lz px is iota h cut py. Similarly, if we commute Lz, if you find Lz py, you can put them here and expand. You see that it is minus iota h cut px, and Lz pz, it is 0. And if we use these three in here, where we will have to expand this Lz px squared, and similarly this Lz py squared and Lz pz squared, and substitute, you can see that Lz p squared is equal to 0. If you like, let me work it out in a little bit detail. Lz px squared plus Lz py squared, Lz pz squared. So this I can write, so this is nothing but px, so we can write px first here, then px on the right side. Similarly for this, py, and this Lz pz is 0, so I'm not going to expand it. Okay, this Lz px is iota h cut py, so I get iota h cut px py, and this Lz px is again minus, right? So this is still plus iota h cut px, so this is py, and this is px. So here this Lz py is minus iota h cut px, so I get minus iota h cut py px, and this is nothing but minus iota h cut px py. So this px py cancels with this one, and this cancels with this, and we get 0 as I have written here. So now we have seen that Hamiltonian commutes with this term also. Let's now see if Hamiltonian commutes, the orbital angular momentum commute with this term, and now we have to see if orbital angular momentum component commutes with this potential term. For this, we really have to show what's the commutator between Lz and, let's say, this vector, this magnitude vector r. This is the only thing we have to show, because if it commutes with this magnitude r and that potential is function of r, we can write it as a Taylor series of powered series of r, which means that if it commutes with r, it will definitely commute with any power of r, and we would have shown that it commutes with v of r. So for this, we need to begin first with this thing. Let's see what this Lzx is. So this Lzx is minus y px plus x py x, and this can be written as minus y px x. So I combine this and this plus this and this, x py x. Now we can expand this. Let's write this y first, pxx, and then we have to write this y here and px out. Similarly for this, x okay, x px is iota h cut, so pxx is minus iota h cut, so minus minus plus iota h cut y. This yx is 0, pyx is 0, and this is 0. So this Lzx is iota h cut y. Similarly, you can see that Lz and y, this is minus iota h cut x, and Lzz is 0. And then using these, we can then easily show that Lz commutes with x square y square plus z square, which is this. And from this, since this is r square, it means it commutes with r as well. And if it commutes with r, it means that Lz commutes with any function of r. And since our potential is a central potential, which means it only depends on the magnitude of r, so Lz commutes with v of r. Therefore, we can now conclude that Lz commutes with the two-particle Hamiltonian, where Lz is the angular momentum around the center of mass. Okay, so if this is the case, we can now conclude that the expectation value of the orbital angular momentum does not change with time, because this was equal to iota over h cut Lz h this commutator, which is 0, and this LZ is independent of time also, so it means that the expectation value of LZ is 0. The expectation value of LZ is a constant. Now, LZ is constant. Therefore, the expectation value of the Z component of orbital angular momentum is conserved in quantum mechanics. And since the Z axis that we took was arbitrary, we can as well show that the Hamiltonian commutes with the X component of orbital angular momentum, and Hamiltonian commutes with the Y component of the orbital angular momentum, and similarly that this is also constant. The expectation value of Y component is also constant, and hence the orbital angular momentum's expectation value is conserved in quantum mechanics. That is, it doesn't change with time. Therefore, we saw in this video that translational symmetry gives rise to the conservation of linear momentum, and the rotational invariance gives rise to the conservation of angular momentum. Similarly, this concept we will see that appears in many places, that different types of symmetries of our Hamiltonian always give rise to a particular conservation law. Thank you.